You remember at the end of the previous lecture, I told you that we are about to reach the sort of like the top of the semester, right? Sort of like the top of this top of this mountain of electromagnetism, right? So that's why I put this picture, right? Um, because today we are about to write the finally the foundation of electromagnetism. We're going to write Maxwell's equations. And again, you remember I keep telling you, what does it mean to have a foundation of in some subject, right? Some direction of physics. It means that if you have those set of equations, using them, you should be able to explain any electromagnetic phenomena in the universe. You see something, for example, rainbow, right? You should be able to grab these equations and explain why that happens. Or you see something over there, right? Some another unknown electromagnetic phenomena, right? So you should be able to grab your equations from the foundation, and you should be able to explain that. That's what it means to have a foundation, right? So, and today we will finally be able to write that set of equations, right? Okay, so like reaching the top of the mountain. That's why I put this beautiful picture. It's a photo of Amadablam mountain in Himalayas, right? It's right next to Mount Everest. It's considered one of the most beautiful mountain in the world. Okay, so these are sections which we're going to discuss, and let's revisit Ampere's law. And in a few minutes, you will understand why we want to revisit. But for now, let's just revisit it, right? You remember you used it in your second midterm exam. So what we had? Integral over a closed loop, right? Every time we would pick an Amperean loop, right? Closed loop of B dot ds, right? Must be equal to universal constant mu naught times an enclosed current. And again, integration is done over a closed loop, any closed loop, in which we called an Amperean loop, right? And let's look at this enclosed current one more time. So how did we? What was our procedure of finding an enclosed current? What did I tell you? I told you something like this, right? Enclosed current is any current which is physically embraced by our chosen Amperean loop. If current is within our Amperean loop, then that current is enclosed. Right? It's so from the mathematical point of view, it's such a lousy definition of the process of finding the enclosed current. It's like, oh my God, right? But from the educational point of view, it's better to introduce complicated stuff in steps. First oversimplify it, and then maybe next step, or maybe in a couple of steps, you can introduce a strict rule how this or that can be found, right? So here the situation. So first we use kind of very lousy definition of the process of finding an enclosed current. But today we need to define it properly, right? So that mathematicians wouldn't be ashamed of us hearing what we used before. Right, so strict definition. Again, as usually, first we need to pick an Amperean loop. It's a first step, right? An Amperean loop is needed to handle this integral and, of course, to find an enclosed current. So first step, you pick an Amperean loop, right? Okay, let's assume that this is our Amperean loop. We picked it, right? Second step, you need to choose or pick any, the keyword, any surface enclosed by the Amperean loop. In this case, it can be, for example, a flat surface, but of course, it must end on the Amperean loop. It can be a flat surface, or it can be a baggy type surface like this, but again, it must end, the surface must end on the Amperean loop. So the second, or it can be more complicated, like this baggy type surface, or maybe on that side, right, baggy type surface. And you should be able to pick any surface. And then the last step, if a current physically crosses your chosen surface, if you have a surface and current is basically a line, right? So you should be able to find easily if there is a point of intersection or not. Surface and a line. Okay, so you pick the surface and now your current. If your current physically crosses that surface, then that current is an enclosed current. And I emphasize on the word any surface. So you should be able to pick any surface your soul desires, right? All right. And everyone, it doesn't matter which surface you pick, should be able to get exactly the same current, enclosed current. It's sort of, at this point, we can say we are following that Civil Rights Act of 1964, according to which we're not supposed to discriminate people based on their religion, color, gender, right, and so on and so forth. And now we can add an additional item, right? We're not discriminating based on the choice of their surface to find an enclosed current. It doesn't matter which surface you pick. Everyone should be able to end up with the same answer. It's a I don't know, wonderland, right? It doesn't matter which choice you made. The result must be the same for everyone, right? It's a dream world, right? A Disney world, right? But anyways, that's how it works, right? Again, you should be able to pick any surface, and you should be able to get exactly the same enclosed current. It doesn't matter which surface you pick. Again, 3 steps, let me repeat. First, you pick an Amperean loop. Then you choose any surface you want, but again, it must be enclosed by the Amperean loop. So basically, it must end on the Amperean loop. And then the last step, the third one, if current physically crosses your chosen surface, that current is an enclosed current. Okay, so that's the strict definition of the process or description of the process which we have to use in order to find an enclosed current. Okay, so that's now we shouldn't be ashamed in eyes of mathematicians, right? Okay, so now let's apply this. After defining this process, so now let's look at the cases which we used a few weeks ago when we applied Ampere's law. And we applied for which cases? We had a straight wire with a current, right? And okay, let's pick our typical Amperean loop, and it was a circle centered on the wire, right? You remember we've done it gazillion number of times. Okay, and so now we have first step, we've made the first step, we picked an Amperean loop. The second step, we need to choose any surface you want. You remember, again, no discrimination, you should be able to pick any surface you want, and everyone should end up with exactly the same enclosed current. So let's say you like simplicity, right? Okay, the simplest possible surface is a flat one. Flat one, of course, within an Amperean loop, enclosed by the Amperean loop. Okay, sort of like, let me pick this purplish color, right? So that's our, okay, let's say your chosen surface. Let's call it S1, flat one. Okay, so now the last step, which current physically crosses that surface? It's obviously that current I. That current I crosses this surface, purplish surface at this point. So that's our, okay, yours, enclosed current. Okay, your I enclosed is I. Okay, let's now my choice. Let's say I like to overcomplicate stuff. Okay, and I will pick, instead of a flat surface, I will pick some baggy type complicated surface like this, for example, right? And again, you must understand, it ends on the Amperean loop, right? It's sort of like this, my surface, right? It ends on the Amperean loop, but baggy type. And of course, it goes much deeper into the space, right? So that's my surface. Let's call it S2. So now the last step, so I picked the Amperean loop, I picked the surface. The last step, which current physically crosses this surface? The same current I. So you see, I'm getting exactly the same enclosed current as you got. So we both got that I enclosed is I. So if you apply Ampere's law for using both of these surfaces, we all will end up with exactly the same answer. Great, it worked. Ampere's law works for these cases, right? And that's why we used it. Oh, and at this point, Maxwell came. Speaking of geniuses, troublemakers, every time they think too deep, they disturb the nice life, settled life, creating troubles, right? And we've observed something like this when we introduced Faraday's law. You remember, up to that point, everything was great, right? Our equations could explain everything, and then Faraday came, experimental geniuses, and he observed some phenomena like production of current, which couldn't be explained by any of those equations, right? And as a result, because of his geniuses, we needed to introduce a new fundamental law, Faraday's law. And now it's time for a theoretician to create troubles. Maxwell, he was great genius, right, in theoretical physics, right? So he found a trouble. What did he observe? Actually, it was good that Maxwell was born in the 19th century. If he was born a few hundred years before that, he would probably end up like a Giordano Bruno, right? So anyway, what did he What did he find? So he said, you know what, your example is too simple. Let's look at a more complicated example. Let's add a capacitor to this circuit. Okay, part of the circuit. So again, we will have a capacitor, right? A positive electrode, right? A negative electrode, right? Plus Q minus Q, right? Of course, there will be electric field E between these plates, right? And our current. Let's assume this capacitor is being charged with current I. And of course, current I also leaves the capacitor, goes that way, right? Okay, so he said, you know what? I want to look at this situation and apply Ampere's law like we applied it just a few minutes ago. Right? Again, let's pick the most convenient Amperean loop. There it is. Again, centered on the wire, right? And let's try to use our surfaces, right? Again, in order to find I enclosed. Again, the first step, we pick an Amperean loop. Now, let's say you pick your flat surface, right? Again, flat within this Amperean loop. Okay, so it will be that, again, that purplish color, right? So that's your surface S1. And now, if you apply Ampere's law, right? I know, first of all, of course, we need to finally make a decision which current is enclosed. Again, physically, this current I crosses your surface S1 at that point, so I enclosed is I, right? So again, as a result, you can write Ampere's law, integral of B dot ds equals mu naught I enclosed, and in this case, I enclosed is I. So now I will just rewrite this law, but now instead of I enclosed, it will be our current I. Okay, that's what you get using your surface S1 to find I enclosed. But you know, Faraday said, wait, not Faraday, Maxwell said, you know what, it's too simple. He overcomplicated stuff significantly more. He said, you know what if I pass my surface through the gap between the plates of the capacitors, between the plates of the capacitor. For example, like this. And again, you must understand that this surface ends on the Amperean loop, right? On the Amperean loop. So pretty much for this surface, here is sort of like there is no surface S2, right? So the surface S2 is over here, right? And here is sort of like an opening. Okay, so he picked this surface S2, sort of like it's this orangey surface, right? And So now, which current is an enclosed current? Again, which current physically crosses this surface S2? There's no current. There's no current crossing this surface S2 because this current I goes through this hole, right? So current goes through this hole and ends up on the plate of the capacitor. But the surface S2, which Maxwell picked, goes around the electrode, right? Around the electrode, and of course, this is the gap, surface S2, there is no surface S2 over there, right? Now, I enclosed is 0. As a result, so if you apply Ampere's law, but now for the surface S2, so the left-hand side will be the same, but the right-hand side, now I enclosed is 0 because physically this current I doesn't cross surface S2. So I enclosed equals 0, and as a result, integral of B dot ds equals to 0. How come? Something is fishy. Look, the left-hand sides are the same because, yeah, we integrate over the same Amperean loop, right, in both cases. But the right-hand side, here we have mu naught I, here I. See, here is 0. Of course, it's impossible, right? Left-hand side's the same, right-hand side's different, right? Troubles, right? And where is the trouble? Obviously, something wrong with Ampere's law. Of course, it must be adjusted, right? And which part of Ampere's law failed to work? Left-hand sides are the same, and there's nothing wrong with the left-hand side. Left-hand side, we integrate over the same Amperean loop. But the right-hand side, yeah, we have mu naught I, and here we have 0. So something wrong with the right-hand side. And obviously, there's nothing wrong with universal constant mu naught, right? You cannot do anything with the universal constant. It's obviously some additional current is missing in this equation, right? And so when Maxwell looked at this example, and since Ampere's law failed to work, it means that in that form which we used Ampere's law is not a fundamental law. If you find any single example in the universe, and if that example, your fundamental law fails to work, it means that law is not fundamental. So in that form, Ampere's law is not a fundamental law. So I lied to you. Right? But of course, from educational point of view, it was okay, right? So it means that it must be adjusted somehow. It must be fixed, right? And again, I think I convince you that some additional current must be added to the right-hand side in order to fix this law, right? Okay, so what is usually done in situations like this when, I don't know, theoreticians find something where something doesn't work? The first reaction is to fudge something, construct something, right, and then try to fix it and see if it works, right? And then if it does work, then you can justify, you create the story, right, and later on you can derive it somehow more properly, right? But first, usually it's a fudging, right? Trying to fix it, hoping that it will work, right? And then, of course, if you win, if you explain, and then you can create a great story, right? How, I don't know, you were sleeping and God came to you in your dream, right, and explained to you how it should be fixed, right? And since you're the winner, you will get standing applause anyway, right? All right, so what did Maxwell do in order to fix this law? So obviously, he needed to construct an additional term which has units of current. And obviously, it failed to work in the presence of a capacitor. So he decided to construct an additional term which has units of current. Okay, let's move to the next slide. All right, it's exactly basically the same picture. I just made it smaller, right? I just copied and pasted, right? So again, we have the current. I enters, we have a capacitor, we have electric field, D is the spacing between the plates, right, and plus Q and minus Q, right? So it failed to work in the presence of the capacitor. So let's construct a new term which has units of current. So how can that be done? For example, first we can write expression for the charge, right? I know, using some terms. Right now it's difficult to tell, right? We're just fudging. We're just using Frankenstein's method, right? Put together something, right? Hoping that it will work, right? So what if we write an expression for a charge Q? And then how can we get a term which has units of current? We have to differentiate that Q with respect to time. And that will give us a term which has units of current. All right. Okay, so let's do it. So where can we get the charge? From the definition of capacitance. You remember, like, months ago we introduced it. Capacitance equals to the ratio of charge divided by the potential difference between the plates of the capacitor. Okay, so of course we can solve it for Q. Q will be equal capacitance times delta V. So beginning, C times delta V. Okay, then next, what are we trying to fix? We're trying to fix the fundamental law. And you remember I told you a few classes ago that fundamental equations, fundamental laws must be written in terms of fundamental quantities. And capacitance, right? Yeah, it's a ridiculously useful idea, right? But it's not a fundamental quantity. No, not at all, right? It's better to get rid of C and write it in terms of something, right? And then delta V, electric potential, okay, potential difference, voltage, right? Again, it's ridiculously useful, right, from a point of view of applications. But if you talk to hardcore physicists, right, they barely use delta V's, right? They usually use electric field, right? Again, let's get rid of delta V and write it in terms of the electric field, this electric field between the plates of the capacitor, right? Okay, and that can be easily done. So first, C. Since we're dealing with a parallel plate capacitor, so we can easily write expression for the C. C, because you remember we derived it. C is epsilon naught. A area, A is the area of the plates divided by the spacing between the plates. So that's what we're going to use instead of C. Now, instead of delta V, we're going to use the formula which we derived many classes ago, right? Potential difference between the plates is E times D. You remember electric potential inside of the capacitor, it's E times S, where S is the distance from the negative electrode, right? So as a result, the electric potential at the negative electrode is 0. That's where S equals 0. And electric potential at the positive electrode is E times D. So as a result, potential difference, ED minus 0, it's E times D. So that's what we have here. That's what I use. Okay, now let's plug it. D gets cancelled because we have here in D in the denominator and in the numerator. D gets cancelled. And as a result, we have epsilon naught electric field times area. Now, question for you. Think for a second. What is E times A? At this point, you should be able to recognize this quantity. E times A. What is this? Electric field, area. It's the electric flux. It's the electric flux. You remember, number of electric field lines crossing a certain surface. Area is given. If area is given, electric field crossing that surface. It's the electric flux. Electric flux through the a side of the capacitor. All right. So it's electric flux. So we're getting epsilon naught times electric flux. Okay. At this point, I'm sure that Maxwell started feeling more and more excited because we're getting something which in structure looks like what we had in Faraday's law. But in Faraday's law, we had magnetic flux, right? rate of change of the magnetic flux. Now we're getting electric flux, and it looks like we're going to get something where we're going to have a rate of change of the electric flux, similarities between the magnetic world and the electric world. It feels like, yeah, we're moving in the right direction. Okay, so now that's the that's how we can write charge. But again, we need to get a term which has unit of the electric current. So in order to get electric current, units of the electric current, we need to differentiate charge with respect to time. dq over dt. Okay, so now let's differentiate it. So I equals dq over dt, and we can differentiate our this expression, epsilon naught times flux, electric flux. So d over dt, epsilon naught times flux, electric flux. Of course, epsilon naught is our universal constant. Of course, we can take it outside of the sign of differentiation, and we will get epsilon naught times rate of change of the magnetic flux. And from the other side, look, when you differentiate charge with respect to time, dq over dt, also from the other side, it is equal to the actual current flowing into the capacitor. So I, right? And from the other side, we managed to construct this additional term. So that's what Maxwell managed to get in an attempt to save Ampere's law. Okay, so he got this term, and of course now this construction we've never seen in this semester, in this course, right? So now what's the next step? We need to give it a nice or cool name. And the name for this term is a displacement current. Displacement current. Okay. If you think, what does it mean, displacement current? All right. If you try to understand the meaning of this term, there is no meaning. Back then, 150 years ago, when this was the hot subject, right, in physics, of course, they tried to imagine or try to model what happens inside of this capacitor, right, in terms of this displacement current, right? And all that model turned out to be completely wrong. It was trashed, right? But name survived. So the model was trashed, but the name survived, maybe because it just sounds cool. So displacement current. So the point is, don't try to understand the meaning of this term. It's just nice name. That's it. All right. And by definition, it is equal universal constant epsilon naught times a rate of change of the electric flux. That's what Maxwell decided to use to fix Ampere's law. And before we adjust Ampere's law, look at very important, important fact. So displacement current on this side of this equation, right? But on this side of the equation, on the left-hand side, it's I, actual current, charging a capacitor. Actual current charging this capacitor. So again, from one side, it's an actual current charging the capacitor. I don't know, 5 amps of current flows into the capacitor. And from the other side, on the right-hand side, we have our displacement current. So numerically, our displacement current equals to the actual current. But they're equally just numerically. It doesn't mean that their natures are the same. In order to understand what I mean, look, a simple example. Let's say I have a big elephant. Its mass, or his mass, her mass, its mass, let's say 5,000 kilograms, 5 tons. And here I have, let's say, I don't know, a bunch of mice. I don't know, maybe a few thousand, whatever. But their mass, let's say, also 5,000 kilograms. We can say that mass of an elephant equals to the mass of these mice, right? 5,000 kilograms equals to 5,000 kilograms. Numerically, their masses are equal, but their natures, of course, completely different. This is an elephant, these are mice, right? The same here. This is an elephant, right? Actual current, let's say, and these are mice, right? Displacement current. So they just numerically equal. 5 amps, 5 amps. But again, they have nothing in common in terms of nature. Right? but numerically equal. It's very important. We need to remember that. The way we derived it, not derived, it's the wrong word, the way we introduced this displacement current, right? Okay, so now that's, as I told you, that's what Maxwell decided to add. And so now, new form of Ampere's law, new form of, or adjusted Ampere's law. Integral, left-hand side is exactly the same because there was nothing wrong with the left-hand side. Integral over the closed loop, Amperean loop, B dot ds equals mu naught times. Now, we have I in. It's okay, still enclosed current, but by this I enclosed, we mean actual current, which is a flow of charges. Like, okay, in this case, this I, it's the actual current, which is a flow of charges through the wire. And now Maxwell added newly introduced displacement current, whatever nature is behind this displacement current. But I can jump ahead and tell you immediately, right? So what's the nature of this displacement current? Changing in time electric field. Okay, here it's a changing in time electric flux, but if you dive inside, of course, there is an electric field. It's a changing in time electric flux. That's what behind this. That's the nature. Okay, and of course, we can write explicitly, right? Instead of I sub d epsilon naught rate of change of the electric flux, and this is a modified form of Ampere's law. And since Maxwell, who found the problem, and he managed to fix it, of course, so he managed to add the term, and his name was added to the name of this law. So now it's Ampere-Maxwell's law, right? And it's quite common in physics, right? If you in the future manage to find an example where this Ampere-Maxwell law fails to work, and if you manage to fix it, then your name will be added, right? I know, Ampere-Maxwell-Smith law, right? If you find something else, right, then there will be another hyphen and your name will be again added. Like when I was an undergraduate student, we had a professor who taught for us quantum theory of solid state physics, right? And he was a star in solid state physics, right? Okay, not the brightest star, but star, right? And there was one equation, and the name of that equation consisted of 4 last names. First last name, hyphen, second last name, hyphen, third last name, hyphen, and then there was a name of our professor, right? So there's even more complicated situations like this, right? Right. Here you have only 2 names, Ampere-Maxwell law, right? Okay, so that's how Maxwell fixed this law. Okay, so now let's look at properties of this displacement current, because right now it's a very mysterious current, right? Okay, it's exactly the same picture, basically. I just copy it and paste, right? First, first probably I need to open the definition of the displacement current, right? Okay, what can you say about the displacement current outside of the capacitor? Over here, for example. If it sounds confusing, look, what is inside of the definition of the displacement current? Electric flux. Of course, electric flux, it's a electric field times area. What's the value of the electric field outside of the capacitor? You remember at the very beginning of this semester. Electric field outside of the capacitor is 0. So electric flux outside of the capacitor is 0. So the value of the displacement current outside of the capacitor is 0. Right? On this side of the capacitor, and of course on that side of the capacitor over here, of course, displacement current will be 0. We're just getting all the properties possible. But of course, inside of the capacitor, since electric field is not 0, it's uniform, right? So we can, so there will be non-zero displacement current. And we can introduce, right, so direction of that displacement current the same as the actual direction. So we can draw something like this, right? Where is it? Here. I displacement. So it's only non-zero between the plates of the capacitor. So it's a first property. Now the second. Okay, I just heard some noise. I thought maybe there's a question. All right, second. Now you remember our conservation of current, what, a month ago, where I told you if there is no junction point, right, in part of the circuit, then current must be exactly the same. But what if we had a capacitor in that part of the circuit? Current flows into the capacitor. Between the plates of the capacitor, there was nothing, there was no current. And outside of the capacitor, we had again current, that current I. So basically, strictly speaking, back then, we didn't have a true conservation of current if you had a capacitor. But now we have a true conservation of current, even if you have a capacitor. Outside of the capacitor, we have the actual current, which represents the flow of charges, right? Let's say 5 amps. Then between the plates, we have a displacement current, which numerically equals to the actual current. The previous slide, I emphasized on that, right? So again, 5 amps. And then outside of the capacitor over here, again, the same current, actual current I flows, which of 5 amps, let's say. Again, so we have 5, 5, and 5. So current is exactly the same. So now we have kind of true conservation of current, even in the presence of the capacitor, right? Again, it's not that big a deal, but it's good to connect current stuff with the past, right, in order to establish stronger connections between different parts of the course, right? Okay, and again, numerically, displacement current equals to the actual current. And okay, so now, probably the most important. So what's the nature of this displacement current? This displacement current has nothing to do with a flow of charge. Nothing. Nature is completely different, although numerically they're equal. Right? So the displacement current is an equivalent, or maybe we can say, what does a displacement current have in common with the real current? Only two things. They have the same units, units of current, amperes, right? And the second, they produce magnetic field. So the displacement current produces magnetic field, like actual current. These are only two things in common between these two currents. Otherwise, they have nothing in common except for these two pieces, right? So displacement current has units of amp, but it has nothing to do with the flow of charges, because between the plates of the capacitor, there are no charges, right, flowing. So the same units, and the displacement current produces magnetic field like an actual current. So we can call it a current only because of those two things, right? And it produces magnetic field. Okay, next slide I will dedicate to that. Produces magnetic field. What's the process? Okay, not the process. How does it produce magnetic field? Changing in time electric field. Basically, what is inside of the displacement current? The rate of change of the electric flux. Inside of that electric flux, there is an electric field. So effectively, it's a changing in time electric field produces magnetic field. That's why this displacement current can produce a magnetic field, right? Otherwise, there is nothing in common between the actual current and the displacement current, except the same units, and displacement current produces magnetic field like an actual current. Right? Okay, and again, in a couple of slides, we will see that. So this displacement current between the plates produces magnetic field. they are magnetic field lines, or actually we can call that magnetic field induced magnetic field, right? And because of the symmetry, because electric field is uniform, magnetic field lines, in this particular case, magnetic field lines form circles. How can we find direction of those magnetic field lines? Again, right hand rule number 2. Again, outstretch your thumb in the direction of the displacement current and curl your fingers, right? Of course, we're not going to prove that those are circles, magnetic field lines. It's more complicated. But of course, you can, for example, grab the compass needle and convince yourself that magnetic field lines form circles, right? Okay, so now these are properties of this displacement current. And now let's look, because now we need to see if this modified Ampere's law, Maxwell's law, can explain explain those troubles which Maxwell observed, right, in the presence of the capacitor. Let's go back to that example. Okay, right. Here, the picture, I just copied and pasted and made it smaller, right? It's exactly the same picture which we saw 3 slides ago. So you remember there's the current I charging the capacitor, right? And two surfaces, S1, which gave us enclosed current I, and this is surface S2, which gave us enclosed current 0, 0 enclosed current. So now we have Ampere Maxwell's law, and now let's apply it for this situation to see if we fix the problem. Okay, Maxwell fixed the problem. Okay, so let's start with surface S1, your surface, flat surface, this purplish surface, right? Okay, so now we have I in, it's a actual current, and this is a displacement current, right? Okay, so for surface S1 is the flat surface within the Amperian loop. What can you say about these currents? So first current, I enclosed. It's the actual current. It's the same current I, yeah, physically crosses your surface S1. So that's what I open. Okay, that's what I show in my explanation box. I in, its actual current, equals our current I charging the capacitor. Second term, displacement current. What can you say about the value of the displacement current? For the surface S1, displacement current is only between the plates. It doesn't go through your surface S1. So I displacement is 0 in this case. We just discussed it. The property number 1, outside of the capacitor, displacement current is 0. Right? So that's what I can write over here. So I displacement equals to 0. So as a result, for the surface S1, we're getting on the right hand side mu naught times I. Okay, that's your surface. Now Maxwell's surface, which he picked, and that surface goes through or between the plates of the capacitor. Okay, so exactly the same Ampere's law. Now mu naught I enclosed plus ID, but now we use surface S2 to find the value of I enclosed and ID. So now, what's the value of I enclosed, which is the actual current? I in actual current is 0 because it doesn't cross surface S2. Actual current, this current I, goes through this hole, right, and ends on the positive electrode. So actual current doesn't cross surface S2, and that's what we saw 2 slides ago, right, when we discussed the problem. Okay, so I enclosed equals 0. The second term, displacement current, I displacement, it's there. It is between the plates. It crosses our surface S2 because the surface S2 goes between the plates. And you remember, I emphasized in the previous slide and also emphasized on that over here that the value of the displacement current numerically displacement current equals to the actual current flows into the capacitor. So numerically, ID equals to I. As a result, we're getting exactly the same result as we got for the surface S1. So both surfaces S1 and S2 give us exactly the same answer, the same the same current, the same enclosed current at the end. So yes, Maxwell managed to fix the problem. So this form of Ampere's law now is truly universal. Now, yeah, it's truly universal. All right, trust me, cross my heart, right? Okay, so now Maxwell again found the problem and he managed to fix it, right? Okay, so now since it's a very important point, again, I introduce the sort of special slide. Again, you remember what is the structure of all these Maxwell's equations? They have exactly the same structure. On the right-hand side, we have sources, and on the left-hand side, we have a fields which are produced by those sources. Now, magnetic field, which is on the left-hand side, is produced by what? By actual current I in actual current, which is the flow of charges. And second, this magnetic field can be produced or is produced by changing in time electric field. And now you remember that guy? This guy was jumping when we introduced Faraday's law. In the Faraday's law, what we saw? We saw that changing in time magnetic field produced an induced electric field. And now we have a reverse situation. Now changing in time electric field produces magnetic field, induced magnetic field. We have a complete symmetry. Changing in time electric field produces magnetic field, changing in time magnetic field produces electric field. I told you like a couple of classes ago that these two worlds, electricity and magnetism, they're inseparable. That's why we call them electromagnetism. And again, you remember this picture? Eternal dance of the electric field and the magnetic field, which are basically like inseparable, right? If they can reproduce each other, right? So magnetic field can produce electric field can produce magnetic field. Amazing. The world is amazing, right? Okay, so yeah, it's very, very important point. And now we have three equations in the set of Maxwell's equations, right? But no, you know what? Before that, sort of now again, what I just told you, right? What a few classes ago, what we saw that changing in time electric field produces magnetic field. Changing in time magnetic field produces electric field, right? Faraday's law. If you have a solenoid, right, and if magnetic field inside changes in time, then inside of the solenoid there will be induced magnetic field, and the induced electric field produces induced electric field lines form circles, right? And we know how to find direction of those circles and so on, right? So inside of the solenoid we can have induced electric field. And now we sort of introduced a reverse situation. If you have a capacitor and inside of the capacitor there is an electric field, and if that electric field changes in time, then now magnetic field is produced, and we call that magnetic field induced electric field. And again, magnetic field lines are circles, and in order to find direction of the induced magnetic field lines, again use right-hand rule number 2, right? So again, I'm just trying to emphasize on the symmetry between these two between these processes, right? Okay, so now the last equation. So now we have three equations in the set of Maxwell's equations. It's Gauss's law, then Ampere-Maxwell's law, and Faraday's law. But as you know, there are four Maxwell's equations, right? And now it's time to introduce the last one. And the introduction is very short. Okay, let me finish this quickly. Right, extra 1.5 minutes. using the symmetry. You remember we have what? Faraday's law and Ampere Maxwell's law. They both integrals. We have integrals over a closed loops, right? In the Faraday's law, and which in Faraday's law, what allows us to find electric field. So it's a law where we have integration over a loop in the world of electricity. Then Ampere Maxwell's law, we have a law where we have integration over a closed loop to find magnetic field, so it's basically in the world of magnetism. Then we had Gauss's law. In the Gauss's law, we have what? Integration over a closed surface in order to find electric field. So basically this is law where we have integration over the surface in the world of electricity. But you feel like there is a gap. There must be something similar to the Gauss's law, but for the world of magnetism. So that we will have one law where we have integration over a line for the world of electricity, law integration over a line in the world of magnetism, and the same, so integration over the surface in the world of electricity, integration over the surface in the world of magnetism. Right now, the Gauss's law for the magnetism is missing. So now that is the last equation. So I'm introducing that law, logic of that law, using the symmetry between these two worlds, right? So let's recall the Gauss's law for the world of electricity. Integration over the closed surface, E dot dA equals to Q enclosed over epsilon naught. And now I claim that there must be a similar law for the world of magnetism. So instead of electric field, we are going to have here magnetic field. Something like this. Okay, integral over the closed surface B dot dA. And now, can you guess what should we have on the right hand side of this law? On purpose, I left the gap. And if you still haven't recognized what should be on the right hand side of this equation, look what we have here in this Gauss's law. We have charges. What's the fancy name for electric charges? I mentioned it a few times in this course. Electric charges, effectively, electric monopoles. Positive charge, for proton, for example, it's a positive electric monopole. Electron, it's a negative electric monopole. Charges are electric monopoles. So here we have on the right hand side, we have electric monopoles. So it means that over here we must have magnetic monopoles. But what can you say about magnetic monopoles? You remember a few classes ago? There are no magnetic monopoles. So far, no one has observed them. So we need to show that fact that so far since no one has observed any magnetic monopoles, it means that on the right hand side of this law, we must have what? 0. If you, in the future, for example, manage to find any magnetic monopole, this equation will be changed immediately. And you will get Nobel Prize immediately. Right, next year. But so far, since no one observed magnetic monopole, on the right hand side over here we have 0. So that's the last Maxwell's equation. All right, and as a result, all right, next class I will just quickly go through these 4 Maxwell's equations. Right. Okay, guys, thank you.